All right, so far we've recently been talking about examples in SCT2, and we're going to continue to do so today. So the example that we did last time was the pion-photon form factor. That did not have any soft degrees of freedom. It just had collinear and hard degrees of freedom. So it was a particularly simple example of something we could think of in SCT2. We'll start with a slightly more complicated example, this decay, b to d pi, where we have both collinear and soft degrees of freedom. This was an example that we mentioned at the very beginning of our discussion of SCT, and now we're going to see how factorization looks for it. And then we'll talk about something called the rapidity renormalization group, which has to do with situations in SCT2 where the separation of degrees of freedom is a little more complicated than in the previous examples, and we'll see that there can be a new type of divergence that shows up. And that new type of divergence leads to a new type of renormalization group. So b to d pi. So there's going to be, in some sense, three hard scales of this problem. The mass of the B quark and the mass of the charm quark are going to be taken to be much greater than lambda QCD. So we'll have an HQET type description of the B quark and the charm quark. And also the energy of the pion, which is in some sense related to the difference of the B quark and the charm quark mass. We'll also take that to be much greater than lambda QCD. So just by kinematics, this thing is proportional to MB minus MC, roughly. You could say it's the difference of the squares of the hadron masses. OK, so let's first, we know how to treat this decay if we were integrating out the W. This is a weak decay, so B is changing the charm. Integrate out the W boson, run down to the scale MB, which is the largest scale here. That's the electroweak Hamiltonian. So that's what we'll call the QCD operators, which are the relevant description at the scale of order MB. Some prefactor. And I'll write the operators in the following way, a slightly different basis than we used previously, or a long time ago when we were talking about this particular case. So just a different color basis, singlet and octet. OK, so that's our description where P left is projecting us onto the left-handed components. So what we want to do is we want to factorize the amplitude. This is an exclusive process where we make a transition between specific states. So we'd like to separate scales in the d pi, and then we have O0 or O8 in this matrix element. So we have two matrix elements, one with O0 and one with O8. And so what could it possibly look like? Well, we already talked about the degrees of freedom here. The D is going to be soft and the B is going to be soft. So this is soft, this is soft. This is going to be collinear. And so if it's going to factorize and the soft degrees of freedom are not going to talk to the collinear, the kind of thing that you would expect to show at leading order in the lambda expansion is that you have the following kind of process. Let me reclaim this space. So here's a heavy quark. Here's one of these operators. Here's the valence quarks in the pion. Another heavy quark. So this is B, charm, U and D. And there's an antiquark, and we have to address this by gluons. And if it's going to factorize, then the way that we should address it by gluons is as follows. We would have soft gluons here, and they could interact, if you like, between things in the B and the D, because the B and the D are both soft. And we can also have vacuum polarization diagrams. And that is going to factorize from things in the pion, which are going to be collinear. So we have our collinear gluons and collinear quarks inside here, and maybe there's some Wilson lines too. So we would expect some kind of picture like that, and that's actually going to be what we do find. But exactly what happens at this vertex, what kind of convolutions there are, that we have to work out. All right, so what factorization in this context means is that there's no gluons that are directly exchanged between the B to D part and the pion part. So that it effectively factorizes into a matrix element that's like a B to D transition and a vacuum to pion transition. So you can even guess what kind of objects this would depend on. If you have something like this green thing, that's a B to D form factor. So we expect a B to D form factor. And for the pion, if you have something like this, well, we already talked about something like this when we were talking about gamma star gamma to pi 0. So for the pion, we expect the pi 0, the light cone distribution. Which is the sort of leading order operator for the pion. So we'd expect a phi pi of x. And we'll see that we do indeed find that. So the B and D have p squared of order lambda QCD squared for their constituents. The pion is collinear, and its constituents have p squared of order lambda QCD2, but they're boosted. We can again use SCT. This is SCT2, but we can use SCT1 as an intermediate step, just like we talked about last time. So let's do that again. So match, step one was to match QCD onto the sket1. So there's some hard scale, and the hard scale in this case could be any one of these three. So collectively, I just denote them by Q. And so what's going to happen in that matching is we take these operators 0 and 08, and we have to match onto SCT operators. So let me call the SCT operators Q0. Yeah, I guess there's because of the fact that there's a heavy quark and the way that that works, there's two possible spin structures here. But we'll see that actually only one of them has the right quantum numbers in the end. So we have heavy quark fields, charm, and bottom. We can imagine that type of operator. And then for the collinear part, we can dress it with the Wilson line, as always. And let me put the flavor upstairs. And let me put in the most general Wilson coefficient that I can think of for this process. This could also depend on v dot v prime. I didn't denote that, but in general it will. And it could depend on any of the scales q. So it can depend on the large momentum of the linear fields, as always. And there's one combination that's not restricted by momentum conservation. So there's one combination that's not related to these scales. And that's in my notation, the p-bar plus operator. And then likewise, there's another thing with the TA. So same thing. TA, everything the same. TA, and then this has got a different coefficient, like that. And so what are the Dirac structures, just to be explicit? The heavy one, so the light one is going to be m bar slash over 4 in my notation, the 1 minus gamma 5. And for the heavy one, you could have either 1 or gamma 5. And that's because you originally have a left-handed, here you have a left-handed guy between the charm and the B. But remember that a mass term connects left and right? So after you integrate out the mass of these quarks, you don't know the chirality anymore in this. So that's why you could have both the possibilities, 1 and gamma 5. So if you put any other Dirac structure, so here you could use chirality, and so you know that these guys should be left-handed still, and that's why you know that this should be this structure. You know it should be an n bar slash because any other structure that you would stick in here between them would give you something that's power suppressed, because you know that n slash on Cn is 0, and also Cn bar gamma perp mu with any kind of p left or whatever is also 0. So you'd have to have something more complicated. All right, so there's those operators. And when you do this matching, it is non-trivial in the sense that these two operators, it's not diagonal. It's not like O0 goes to Q0 and O8 goes to Q8. As soon as you start adding loop corrections, these two mix, and then they give you some contributions to these coefficients, C0 and C8. Okay? So what you mean by octet operator in the electroweak Hamiltonian is different than what you mean by octet operator in the SCT1 factorized result. But that's just a complication that you deal with when you are doing the matching. This guy can be proportional to the Wilson coefficient C0F and C08, and that's not really a big deal. Any questions so far? Yeah.
So the point of matching scale 1 as an intermediate step is to get the softs?
Yeah.
So you're going to do
That's right. I'm going to do that right now.
So that's
Yeah. So then step 2, field redefinition. In the sket 1. And let me not put superscript zeros. Let me just make it as a replacement. So then we get our Q0 again. And, yeah, OK. For this guy, it's exactly the same. Because in the Q0, 1, 5, all the y's cancel. In the octet guy, it's not quite that way because we do have, in that case, we do have the Wilson lines getting trapped by the TA. So let me write out that case. So we have So that's what we get after the field redefinition for the two operators. OK, so the next thing to do would be to, instead of calling them y's, call them s's. So, but there's one more thing I can do too. So these are, remember, these are soft fields and these are collinear fields. So this isn't factorized because we have contractions between these y's and the fields over here. Gluons can attach to the heavy quarks. So in order to factorize, we want to move those y's from there over to here. And we can do that. So here's how that works. This is a formula that I could have told you earlier. So if you have a y that y's around a TA, that's just actually the adjoint Wilson line. So this is a formula that relates fundamental Wilson lines and an adjoint Wilson line. So in the adjoint Wilson line, you'd build it out of matrices, if you like this. So the matrix indices would be B and C. And instead of having fundamental indices for the TA alpha beta, you have an FABC, and this is the kind of thing that you would exponentiate. But other than that, it's the same thing, and there's just a color identity relating them. So because of this identity, you can also write down another identity, which is y dagger TAY. This guy is, so y dagger TAY is just the other YB. This guy's an orthogonal matrix, TB. So if you reverse the indices, then you get the opposite way. And also this guy is, remember, this is a matrix just in the AB space. So if I use this formula in here, that allows me to take these Wilson lines here and move them over here, right? Because I can take them, write them as a y, and then the y is just something that it doesn't care about. It just moves over because it's contracted with that index A. I guess I've got some problems with capitals and small letters. Let's make them all capital. So then I can move it over here, and then I can convert it back to a y dagger y if I want to. OK, so we can take this guy and this thing and write it over there as HV y TA y dagger HV prime. This is, I don't know if I was careful about that. This is the prime. And then all the soft gluons, all the ultra soft gluons are over here in this matrix element, and all the collinear fields are over there. So if you like, you could say we get this, and then we get our collinear matrix element that has TA, but it has now no ultra softs. And so we have a product of collinear and ultra soft things tied together by one index A. OK, so that's just a little color rearrangement. It's useful because now they're really factorized. And now when we take matrix elements, the matrix elements will factorize. Sorry, before we take matrix elements, we have to switch to sket 2. So this is again an example where it's trivial, because what we have is we have one type of operator that we're considering, this weak transition, and we don't have a time order product of any type of 2 operators in SCT2. We just have a single operator that has both types of fields, and then we have the Lagrangians. So this is, again, simple. So we have one mixed operator plus L0 linear and L0 soft, and those things are already decoupled, and so this is simple. And so we simply replace y's by s, renaming it soft instead of ultra soft. Really nothing is changing. And these collinears, we just put them down onto SCT2 collinears from SCT1 collinears. OK, so to make it look like I've done something, I'll write it out again, but there's really nothing happening. Except that now the fields are in SCT2 with the correct SCT2 scaling. So there's no Wilson coefficient that's generated by this step. There's no additional Wilson coefficient because of that fact. So these are SCET2 now. And similarly for the octet. So here we would really have the OK. So now we can take matrix elements.
Yeah.
Yep.
What do the Wilson coefficients look like when they're not just one?
So they would be functions of, say, plus times minus momenta. So we could have, if it wasn't 1, what would happen is effectively, so yeah, we talked a little bit about this last time, but let me remind you. So if it wasn't 1, that would happen in a situation where you had something like this. Some off-shell field, O, say like this. So this is a T product of 2 things, rather than just one thing that mix soft and collinear. And this field here was off-shell in a way that basically, this field here is an off-shell field that would be a product of the plus and minus momentum of these guys. And so you could get something that's effectively living at this hard collinear scale below the hard scale in the problem from sort of T products of soft and collinear operators. This is I'm being a little sketchy, but since here we only have one operator, that couldn't happen because you just start attaching softs and collinears, but it's already factored. So there's no way that you can sort of get this intermediate off-shell guy. So this guy would be collinear, right? In the way to think about this is like this. This is just a diagram that exists. But then you go over to the SCT2, and then you have your change of collinear to the right collinear, right? But this guy doesn't change. He's still hard collinear.
The matching, when it's non-trivial, actually has a different scale.
Yeah, this scale would show actually up. And so if it doesn't show up, so this would be kind of a situation going from SCET 1. And actually, we could have done some examples where that happens. But I'm choosing to do this rapidity renormalization group instead. Basically, this happens if you look at matrix elements, and you could look at matrix elements where you have some subleading interactions. And there are examples in exclusive decays where you could have this happen. One example is if you look at B0 to D0 pi 0, just having all neutral charges, then actually this will happen. It'll be more complicated than what I'm telling you, but you can derive a factorization theorem for this. It's power suppressed relative to the one we're talking about, because the one we're talking about always has a charge pion. And it turns out that that happens at leading order, whereas the neutral pion process with the neutral B and neutral D is something that's power suppressed. Hope I'm remembering that right. Yeah, I am. All right, so number 4, so this is an aside. Number 4, take matrix elements. And here we find actually that one of the matrix elements is just 0, the one with the octet. So let me write the non-zero ones first. too careful about the two different. About this. So there's some guy that's just giving a convolution between the Wilson coefficient and phi pi, and then this guy, which is some normalization factor times the form factor. These things are all mu dependent in general. And this thing here is the Isger-Wise function, which is the HQT form factor. And W0 is kind of the kinematic variable that that form factor can depend on, which is v dot v prime, the labels on the fields, and that encodes the momentum transfer, which here is just related to the kinematics. So W0 is some function of md and mc, which I'm not going to bother writing down. Just some constant. I mean, it could have some kinematic factors that makes up the dimension, like some, depends on my gamma. Yeah, it's just some number. Okay, so these are the singlet operators. So in the singlet case, we have initial state and final state. In all cases, we have initial state and final states, which are color singlets. And these operators are color singlets. In the case of the octet, we also have color singlet states, and we factorize them such that we'd have a matrix element, for example. So let me just write one of them. And well, and this is 0, because there's nothing that could carry the index A in this matrix element. Okay, so the octet matrix elements are 0. It's important that we factorized it for that to be true, right? If we had d pi, then we'd have a color singlet operator here, B. So we wouldn't have been able to make this statement in the original operator in the electroweak Hamiltonian. This would just not be true. But once we factored it and put all the ultra-soft fields here, everything that's going to be contracted together, then we can make this statement. We couldn't even really make this statement when the y's were on the other side, right? We had to move them over here to ensure that the statement is completely true. Okay, so color octet operator, color singlet states. Okay, so then you just put things together, and we can multiply these two things to get the final result. So if we write it as a matching from the electroweak Hamiltonian, there's some normalization factor, so grouping together these factors of f pi, e pi, and n prime, which I'm not worrying so much about. There's a Isger-Wise function, and then there's a single convolution between the hard coefficient, which is kind of like our example of the photon-pion form factor, and then this light cone distribution. So we see an example where it showed up in a totally different type of process from the one we were considering previously, thereby showing us kind of the universality of that function. And then there would be power corrections to this whole thing that we're neglecting that go like lambda QCD over those hard scales. Okay, so this is the Isger-Wise function. And actually, I did write down what the W would be. So this W would be that. You can write it in terms of the meson masses like that. So it's the Isger-Wise function at max recoil. And this function is measured, for example, in a semi-leptonic transition. So you can imagine that the pion distribution function, or properties of it, were measured in the photon-pion transition. The Isger-Wise function is measured in the beta dl nu transition, and then you can make predictions for this beta d pi. Okay, so that gives you an example of how you would use these factorization theorems. So this applies to basically this type of factorization that we've just talked about. It applies to a lot of different things with charged pi minuses, or you can make the pi minus a rho minus, and that wouldn't really change anything. So you could have B0, if you wanted to look at charges, you could have B0 to D plus pi minus, or you could have B minus to D0 pi minus. And there's a third one, which is the one we were talking about over here, B0 to D0 pi 0. So there's three different ways, three different B to D pi transitions, depending on the charges. And what we've derived applies to charged pions or charged rhos. The neutral ones end up being power suppressed. And you can see that kind of from our discussion. There was kind of never, just writing down the leading order operators, well, and maybe you have to work a little harder, but effectively the leading order operators don't make this transition with the two charges being the same, such that you could get a pi 0. So you have to do something more in order to get that case. All right, so questions?
Can you resum log of MB over MC?
You can, if you want. Oh, MB over MC. So MB and MC, we're treating both of them as avoid the same in what we've done. So if we wanted to sum logs of MB over MC, we'd have to do something a little different than what we did. You'd have to first integrate out MB, treat the charm quark as a light quark. You could do that.
Would it make the sket
It turns out that,
analysis different?
yeah, so those are single logs, actually. They're not double logs. And it's related to the fact that you have massive particles. When you have massive particles, you don't get the extra singularity. And people in HQET worried about summing logs of MB over MC for a while. And then after a sort of doing enough calculations, they realized it was totally irrelevant. And you should just not bother. You should just calculate the alpha S corrections, treating MB and MC as comparable, and summing the logs. If you sort of think of leading log as being more important than the order alpha S calculation, that misleads you. Sometimes the sign is even wrong. And so there's sort of a general experience that summing logs of MB over MC in HQET is not even.
Because they're single logs?
It's because they're single logs. I mean, that's one thing that makes it different than, say, the double logs that you would resum in this process. Actually, these double logs are also single logs. So you could decide whether or not to resum them. But either whether or not you do resummation, this is still useful because you could make a prediction for this decay rate, and it works really well. All right. You can actually also make predictions for these decay rates. You can predict actually the relations between the D0 and D star 0 using the factorization, subleading factorization theorem.